Welcome to this quantitative reasoning lesson on sets. We're in the second part called Set Applications, and this is video 3 of 5 on set applications. So in this video, I hope to help you understand the difference between a finite set and an infinite set. Some of you may already understand the difference because those words are words you've heard in math before and other places. So we've talked about the idea of a cardinal number. Let me get my pen straightened out here. We've talked about the idea of a cardinal number. That tells us how many elements are in the set. So if we count the number of elements, we will know its cardinal number. If we can count and finish counting, that set is finite. So if I have this set containing the positive odd numbers less than 10, 1, 3, 5, 7, 9, and set, I can count. I have 1, 2, 3, 4. There are 5 elements in that set, so the cardinal number is 5. So that's finite. Not all sets are finite. It's not possible to determine a number that's the cardinal number for all sets, though. So the positive odd number is less than 1,000 is bigger, but we actually could still count it. And actually, positive odd numbers less than 1,000, half of those numbers are going to be odd. So 1,000 divided by, you could say, well, we know that's 500 because half of 1,000 is odd. Half of the 1,000 are odd. So you would say 500 is the cardinal number for that set, or you could just write them all out, which seems a lot longer. It's better to find an algorithm. But that is still finite, even though it's really big. But if I just say the set of positive odd numbers, and I don't say up to 1,000 or less than 1,000, now you don't know when to stop counting. So you start counting, you got 1, 3, 5, and you go, so you 1, 2, 3, 4, 5, but this ... means this goes on forever. This set, this ... at the end, means this set is not finite. It is infinite. It has an infinite number of values. So what if I said, well, 1,053 is the biggest odd number? You say, no, I can add 2 to that and get 1,055. And no matter what odd number I think I'm done with, I can add 2 and get a new one. And so that set is infinite. And those 3 dots are called an ellipsis. And that's what we use to say a set is going on forever in this pattern. Now, if I put an end to this, there's another way to use this ellipsis. If I do 1, 3, 5, ... and I put comma 21. This is not infinite. These dots just say continue this pattern up until 21. You would be able to count those. But if the 3 dots are at either end and there's no bookend on the other side to tell you where to start or stop, then that set is infinite. So a finite set is a set that has a countable up to a certain number of elements. An infinite set is one that you cannot ever finish counting. So when you get into upper level math, you get into some abstract algebra, you learn there's actually countable infinity and uncountable infinity. But I'm not going to get into that. It turns out the set of integers or odd integers, or positive integers, is actually countable infinity because you can assign a number to each one. But the set of real numbers is not, because you can always find a space on the number line between the two you just counted, and you can't ever count all of those. That's a detail for an upper level course, though. Right now, I just need you to know that finite set, you can count the number of elements. An infinite set goes on forever and cannot be counted. So, okay, and this slide gets into what I was just saying. See, I got ahead of myself. Not all infinite sets are infinite in the same way. This is not anything we're going to deal with, but it is interesting. I know some of you are interested in some of those more like stranger, more out there abstract math concepts. This is a concept of whether something's countable infinite or uncountable infinite. If you had a number line, you put a tick mark at each integer. -2, and this goes on forever, -3, all the way that way and all the way that way. -1, 0, 1, 2, 3, ... You could count like that, but what if I said, well, count all the real numbers? You could say, well, I've got 0 and 1, then I've got 1 here halfway between, another one halfway between. Even for the rationals, you couldn't count them. They're uncountable also. There I got another one, and each of these little increments is another one in between, and You couldn't even count all the numbers between these two spaces. You couldn't even assign a value because you couldn't go in order. So it's the idea of countable infinity versus uncountable. What you need to walk away from this lesson with is knowing whether a set is finite or infinite, though. Don't worry about whether it's countable or infinite. I won't ask you that. So mathematically, we say things in particular ways to have particular meanings. The number of elements in the set of all integers has a one-to-one correspondence with the natural numbers. We count with natural numbers, so I could make a one-to-one correspondence, and I don't have to go in order. I could start with -5 and then count -2 next, but I could assign a number to each number. It can be assigned to a unique element. So that is, anything that's countably infinite has this property too. But right now, I just want you to understand that finite means you can count how many things there are. Infinite means it never ends. So uncountably infinite can't be done with this one-to-one correspondence. There was a mathematician named George Cantor. You may have heard of Cantor sets. He demonstrated that real numbers is uncountably infinite. If you're interested in looking into that, you could Google George Cantor and see what kinds of things he did. He did some interesting things with fractals also. So even though there's an infinite number of both integers and real numbers, there are actually more real numbers than integers because there are many real numbers in between two integers. Even though they're both infinite, one is more infinite than the other. That's an interesting abstract. Don't worry about that too much. So this is what you need to be able to do. Consider the set C, whose members are positive numbers which are multiples of 10. I don't know if you remember what multiples are. It means, multiples of 10 means 1 times 10 is 10, 2 times 10 is 20. So I can multiply 10 by something and get that number. I can multiply 10 by 1 and get 10. I can multiply by 2 and get 20. So 10, 20, 30, 40, 50, and so forth are multiples of 10. The question is this set finite or infinite? Well, if I write them out, I'm never done. I can, because every natural number, the set of natural numbers, the set of integers even you can use for multiples, goes on forever. So I'm multiplying 10 times each one of these, so that will go on forever also. The pattern continues forever, therefore it is an infinite set. Okay, so what about the following set? Now, here is some interesting notation. This is set builder notation. We have another video that goes into this. So my set D has elements T, has numbers T that are elements of the natural numbers such that T1 is less than or equal to T, which is less than 5. So 1 is going to be in the set. We're using the natural numbers, 1, 2, 3, 4. Don't worry too much about this. I get into that in another video. I think you've already done that, the set builder notation video. So T is an element of N such that they really only need that line there once. 1 is less than or equal to T less than 5. So you do include the 1, but you don't include the 5 because it didn't have that little equal sign there. So I write out the list in roster form, and I certainly can count them. This ends. This has a beginning and an end in its natural numbers, so it's countable. This is a finite set. Okay, that is all I have for this third video. Join me next time when we talk about subsets and proper subsets, and I'll see you in class.